Mr. Tarrou, in this lesson we are going to learn how to find the point of tangency when we are given a tangent line, the equation of it, and the equation of the circle. I'm going to do this video a little bit different. By the way, it's going to be sort of like an Algebra 1 geometry, maybe a beginning Algebra 2 scale, but mainly Algebra 1 and geometry. I'm going to develop the example with you, and by doing that we're going to review how to graph a line. We have one in standard form. We're going to put it in slope-intercept form, do a little reviewing of graphing a line. We're going to talk about the relationship between a tangent line and the radius of a circle, and explain a little bit, where the equation of a circle comes from, a little bit of use of Pythagorean theorem, and then we're going to have the example set up probably in about 10 minutes. But if you want to skip the setup of the example and just see the work of finding that point of tangency, we're going to do that two different ways, by the way, as well. You'll find a timestamp in the description of this lesson if you want to just skip ahead. Okay. Now, the equation of this line, this is going to be our tangent line, is x minus 3y is equal to -3. To graph a line in standard form like this is, you're going to want to use x and y intercepts. If you want to find the x-intercept, by letting y equal 0 and solve for x, and you're going to find the y-intercept by letting x equal 0 and then solve for y, and then you can plot that x and y-intercept wherever they are and draw a line through it. But we're going to put this into slope-intercept form, y equals mx plus b. So we're going to do that by subtracting both sides by x and getting -3y is equal to -x minus 3. We're going to undo that multiplication of 3 by division. And -3 divided by -3, of course, is y. We've got a coefficient of 1 in between the negative and the x, so that's of course -1 divided by -3 is positive 1/3. Don't make that into a decimal like so many students want to do. Fractions are not bad. You can't use a tape measure or a ruler if you can't use fractions. And, when you look at this y is equal to mx plus b, this equation of a line in slope-intercept form, the number that's in front of x is going to be your slope, or m. And that's a rise over a run. Slope is rise over run. So you need those two numbers so that you know how to plot your next point after you plot the y-intercept, which is this number at the end, this y-intercept of 1, this constant, this b, which is equal to 1. So this line has a slope of 1/3, and you're going to plot that after the y-intercept of 1. So we're going to go up to the y-axis, put a dot on 1, and then we're going to go up 1 and over 3. This isn't really graph paper, so I'm kind of doing the best that I can. Just for purposes of trying to draw this by hand, I'm also going to go down 1 and 3 to the left. A down movement is negative, rise, and movement to the left is a negative run, and two negatives cancel out to make a positive like our slope is, and we have a line that looks something like this. Whoops, hello. Let's try that again. Okay, so here is our tangent line. Now, like I said, we're kind of developing this this example together. I don't usually do that, but since I was only doing one example in this video, and I tend to like to do lessons as opposed to just examples, I thought I would make it an opportunity. That was good. Make it an opportunity to do a lot of review with you. Okay, and that's not exactly perfect because, of course, again, it's not graph paper, and I'm not using a ruler. But there is our tangent line. Well, kind of a crooked one too. Now that we have our tangent line set up, we need a circle, right? Because it says given an equation of a tangent line and an equation of a circle. Well, first of all, how does a tangent line and a circle, how are they related? So here's a line. We're going to remember that tangent lines to any curve, a tangent to any curve, whether it's a circle or a parabola or an ellipse or just some kind of crazy curving graph that maybe you're doing if you're studying, when you get to studying calculus. But we're going to just draw a circle here with my gigantic chalk compass. Oh, okay, here. There we go. Now, if that line were to intersect the circle twice, it wouldn't be a tangent line, it would be a secant line. Now, so there's a circle, there's a tangent, that's ultimately what this diagram over here is going to look like, and I'm doing this to remind you on the side, to remind us that when we have a circle and a tangent line, there's some kind of special relationship. Not only does the tangent line only touch the circle once, but there's a relationship between the radius and the tangent line, at least if the endpoint of the radius is the point of tangency, which is what we're ultimately going to find in this example when we have our example set up. Those line segments are perpendicular. Now we need to remember then some kind of property about perpendicular slopes. Now let's see here. Now the slope of this line, the slope of this tangent line that was given, is equal to 1/3. So this radius, which is going to have a perpendicular slope, well, that perpendicular slope, that's a math symbol, of course, for perpendicular. Well, I'm saying of course. I hope you remember. If not, or if you've not seen that before, that does mean perpendicular slope. Perpendicular slopes are opposite reciprocals. Opposite means change the sign. So this slope is positive, our perpendicular slope is negative. Reciprocal means to just simply flip the fraction. So if our tangent line has a slope of 1/3, then as I try and create an equation, place a circle which will be tangent to this line given to us, that is going to be 3. We're going to take that 1/3 and flip it over, make it 3/1. So I'm creating an example for us. I've got a tangent line. I need a circle. The circle can be anywhere along this line as long as, of course, it's tangent. It only touches the circle in one spot. So I'm going to pick a nice easy point like, well, we had a y-intercept here of 1, 0, 1, and then we went up 1 and over 3 because of the slope. And let's just use that as our point of tangency. So I got the answer to the problem before we've even started because we're creating the example to help you do some other problems in your book. So we're going to work out that perpendicular slope. Again, that relationship between the tangent line and the radius. We're going to go down 3. So down 1, 2, 3. And we're going to go over 1. And by the way, I'm also, again, this is the second time I've reviewed with you in this lesson in setting up this example of how to graph a line. To graph a line or to come up with an equation of a line, the minimum requirements are to have a point and a slope. You graph the point, a point the line goes through first, and then from there you do some kind of movement dictated or directed by the slope, and you just draw a line through the 2 points. Now I'm not drawing a line, I'm drawing a line segment because that's going to be the radius of our circle. And so we have a circle drawn that's almost tangent, almost kind of didn't really touch it there, but close enough. We have our drawing then for our problem, and again it says given the equation of a tangent line and a circle, so we have a circle drawn, but what's going to be the equation of that circle? Well, what's special about the shape of a circle? Every single point that the circle is consists of or makes up the circle is an equal distance to the radius. So if every point is an equal distance to the radius, it kind of makes sense then that the equation of a circle comes from the distance formula because all of these distances are equal. So the distance formula is d is equal to the square root of x sub 2 minus x sub 1 squared plus y2 minus y1 squared. Well, that's the distance formula though, not the equation of a circle. So we're going to square both sides and get d squared is equal to x sub 2 minus x sub 1 squared plus y2 minus y1 squared. And these subscripts are not really, they don't have any math operation behind them. They're just a name. Point 1, xy, and point 2, x sub 2, y sub 2. Now, these lengths going from center to circle, of course, are the radius, not the diameter. And if we leave the letter d in there, it's going to get confusing with a diameter, which, of course, goes all the way across a circle. So it's going to be r squared, the radius of the length of that radius squared, is equal to x minus h squared plus y minus k squared. That is the standard form of a circle that you would find in your book. And h and k, you'll notice I lost the subscripts from x sub 2, y sub 2 that we had in the distance formula. I just wrote x and y. And that x and y is going to stay there in our equation. The x and the y in the equation of a graph, that's what describes, it shows your independent and dependent variable, your input and output variable, but it just describes every single point that makes up whatever it is that you're graphing. It's just any generic point. We give some special labels to x and y axis, intercepts and all that kind of good stuff, but x and y represents every point that the graph goes through, that you plug in some kind of independent variable x and you get out a y, and together that makes a point. So you need that x and y in the equation of your circle. And h and k represent the center. It's the x-coordinate of the center and the y-coordinate of the center. And so now that we see how this is drawn, we can see that our center from the origin is over 4, 1, 2, 3, 4. And the center has a y-coordinate of -1. Great. So now I've got something squared is equal to x minus 4 squared plus y minus. Notice I'm going to use a parentheses around that value that I'm substituting in that has a negative. You also want to do that when you're substituting expressions into another equation or another expression to make sure that you get your signs and the distributive property all correct. Squared, because there is a minus sign from the formula, and there's another negative sign coming in from the -1. And a negative times a negative, because there is basically a little -1 there, times -1 is +1. Those are going to cancel out, the two negatives. If there's no exponents or other division signs, nothing else going on, those two negatives are going to cancel each other out. And we have what's left here on the left side. I'm just going to clean this up a little bit. On the left side, we need to figure out what the radius is. Now I said, if you wanted to, hopefully you're watching this development of my example, I said we needed to do a little bit of review of Pythagorean theorem. Well, for plotting this circle, we started with this point at, what is that, 3, 2, and we went down 3. And I'm not going to write -3 because that negative is just for an indication of direction by going down, but it is a positive, it is a length. Lengths have to be positive. It's a length of 3, and this little segment has a length of 1, and we have a right triangle. And how do you find the missing length of a right triangle when you're only missing one length? You've got two legs, the two sides that come together to make the right angle, and you're missing the hypotenuse. Well, if you're missing one side of a right triangle, you're going to find the third side, or that one missing side, by doing Pythagorean theorem, which is a squared plus b squared is equal to c squared. One leg squared plus another leg squared is equal to the hypotenuse squared. That hypotenuse is going to be the radius of our circle. So we have 3 squared plus 1 squared is equal to c squared. The unknown value is not alone because it's unknown. I'm not keeping the two numbers together because I know those numbers. I'm keeping the two numbers of 3 and 1 together because they make the right angle. They are the legs. If I knew the hypotenuse and I was missing one of the legs, then my variable would be over here with, maybe like 3 squared plus b squared is equal to, something else, 7 squared or whatever it is. Okay, so 3 squared is 9, plus 1 is equal to c squared, and 9 plus 1 is equal to 10. And I really don't need it, but of course if I want to solve for c, I don't need to do this extra step. I'll explain why in a second. The opposite or the inverse math operation to squaring a number is square rooting. We square root both sides and we get the square root of 10 is equal to c. The c, the hypotenuse of the right triangle in here, is our radius, so our radius is square root of 10. But see, it was r squared. Basically, it was c squared, and we knew what c squared was here. It was 10. Square rooting and squaring, those are inverse math operations. So the equation, now we're done setting up our example that I'm now going to help teach you how to find the point of tangency, even though we already know it. It's 3, 2, but of course normally you would not. We've got our equation of a circle. We have given to us an equation of a line. Let's get all this cleaned up and see how we would approach the problem if that's what we were given, which is the point of this problem. No, 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 no. Alrighty then, we've got our example set up, and we have the equation of a tangent line given, and we have our equation of the circle, and pretending like we don't already know the answer, and also that we didn't just draw this and realize that visually it looks like it's an easy answer to arrive at, and then it looks like it's 3-2. How would we do this problem if it wasn't easily worked out, if we didn't already know the answer? Well, you might have already learned how to solve systems of linear equations through the substitution method or the linear combination method. And I'll put a link in my lesson here if you would like a little refresher on those techniques, or maybe just learn them if you haven't yet. You probably have if you're watching this lesson. So you know that all we're doing is finding an intersection point between a circle, which is not linear, but the intersection point between a circle and a line, and we see that y is equal to 1/3 x plus 1. I can just take that expression of 1/3 x plus 1 and plug it into the other equation for y, and I'll have that one equation in terms of only one variable. But the process of solving this problem that way is going to be a few more algebraic steps and having to deal with that fraction a bit more than what we're going to do right now. And what we're going to do to solve this problem is focus on the concept that we actually already reviewed when developing this example, which is another reason why I wanted to show the development of the example. A tangent line and a radius at the point of tangency must be perpendicular. So the slope between this unknown point of tangency, x and y, the slope between that point and this point of 4, -1 needs to be equal to -3. Now, where am I getting the -3 from? Well, I'm going to look at the equation of my tangent line, and I'm going to say, okay, well, my tangent line has a slope which is equal to 1/3, because, either you have put the equation into slope-intercept form from whatever form, like we did with standard form, or it was already given to you in this form, and you can just see it's y equals mx plus b. So the perpendicular slope is, of course, that we already used it to develop the example, -3. So the slope formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And that means that we've got y minus, I'm going to call this, let's call this the second point, and let's call this the first point. Okay, and I need to get this out of the way so I can keep writing. Okay, so we have the slope of that radius was -3. And the slope of the radius was, oh, well, I kind of need this up here just for a second. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And cleaning that up, we get -3 is equal to y plus 1 over x minus 4. We're going to multiply both sides by x minus 4. But when I write it like that, it looks like it's x minus 4 minus 3. So I'm going to wrap this in parentheses as well, so I don't keep my notation as neat as possible. And we're going to distribute that -3, and we get -3x minus 4 is equal to, now over here, the x minus 4's cancel out because I'm multiplying by that binomial, and we have the division of that binomial, leaving us with just y plus 1. Now we're going to subtract 1 from both sides and get -3x minus 5 is equal to y. Okay. So we have worked out the slope from the radius of the circle, which had to have a slope of -3, and we have an equation that relates x and y together. Well, there's still one equation and two unknowns, so we're still going to need to do some kind of substitution like I alluded to at the beginning here to finish working out this problem. And we have another equation that relates the variables of x and y together, but this is not coming from the same source. This is the equation of the tangent line. This relationship between x and y is coming from the equation basically that, oh, well, how long have you been trying to tell me to stop doing this lesson because I've made a mistake? Isn't negative 4 times negative 3 positive 12? Yes, it is. That's what happens. That's why you need to actually not talk while you're doing your homework and pay attention to what you're doing because you make silly mistakes like that. So when we minus 1 from both sides, we're going to have 3x plus 11. Okay, so I'm not going to reshoot this scene after all. I've caught my mistake. That line, or this equation, y is equal to negative 3x plus 11. Now, plus 11 is way off the course here, but this is the line which is containing the radius. And if I were to continue this up, and if this were a really tall chalkboard, it would cross the y-axis at 11. So here, you might want to, if you need it, of course I'm going to review it with you right now as well, how do you solve a linear system of equations? Well, when you've got an equation of one line, the tangent line, already set equal to y, and you have an equation of another line, that line containing the radius, they're both already set up equal to y, so substitution method is a perfect process to finish this problem. So I'm going to bring this expression for y over here, and we're going to have negative 3x plus 11 is equal to y, which is 1/3 x plus 1. So we're still having to finish the problem using this substitution process for solving a system of equations, but I don't know how you feel this work is seeming so far, whether it's kind of easy or a little bit complicated or really complicated, but I still think it's more straightforward because I'm not having to do all of this foiling of the binomials. I'll give you the other way of working this problem out in a second, where you're not working through the slope, you're just putting them right together and finishing it up. We have an equation, a linear equation, that has a fraction, a division of 3. Now, you can work with that, and I don't think it's really a major problem to work with it, but if fractions just really torment you, just remember that fractions are nothing more than division. So if you have a division of 3 that you don't want, that you find it tedious to work with, get rid of it. Multiply both sides by 3. And we're going to have 3 times negative 3, which is negative 9x, 3 times 11, which is 33. Now over here, what's going to happen is we're going to have 3 times 1/3. Well, to multiply fractions, you go straight across. 3 times 1 is 3. 1 times 3 is 3. And that cancels out to be 1. Or you're just going, hey, dude, I'm multiplying by 3, or dudette. And that multiplication of 3 is going to cancel with the division of 3. Multiplication and division are inverse math operations, and that's just going to leave you with the numerator of 1x plus, and then 3 times 1 is 3. Subtract both sides by negative 1x, and we're going to have negative 10x plus 33 is equal to 3. And sorry about my sort of board usage, I've run it out of room. Let's bring this over here. Subtract both sides. We're trying to solve for x. We're going to subtract both sides by 33. And get negative 10x is equal to negative 30. We're going to undo that multiplication of 10 by division. And x is equal to 3. Now, of course, when solving systems of equations, you're trying to find a point where those graphs intersect, if they do intersect, so that's only half the answer. We need to find out what the y-coordinate of the intersection point is by taking this value of 3 and plugging it into either one of the equations, either this one or this one. Now, I know that has a fraction, but that fraction has a division of 3. So 1/3 of 3 is not going to be very hard to find. So I'm going to use this one. So we have y is equal to 1/3 of 3 plus 1, that's going to be 3 divided by 3, which is 1, plus 1, giving us a y value of 2. So the intersection point, as we knew in the beginning because we created this example together, the point of tangency is 3, 2. And if you remember from the diagram, my fancy picture-in-picture, there it is. We got the right answer. Now I'm going to step off, I'm going to clear all this off, and I'm going to work the problem out for you to just say, hey, you know, we could have just, again, like I said at the beginning of this example, done a direct substitution and solved the problem without, you know, using that relationship between the slope of the tangent line and the slope of the radius, them being perpendicular. I like this method better. You might like the other way better. Let's see. How'd you like the direct substitution? We took that expression of 1/3 x plus 1, plugged it in for y, because that's what it was equal to. We wrote that binomial being squared twice, just so I could show you the foiling, or the, actually I hate the word FOIL, distributing those two binomials together, because the foiling process does not work when you multiply anything bigger than a binomial times a binomial. So like a binomial times a trinomial, or a trinomial times a trinomial, you need to understand that that's the distributive property. Everything in the first group gets multiplied to everything in the second group or factor, and then you move to the next term and you do that distributive property or process over and over again until you connect all of the terms together. And 1 plus 1, of course, is 2. 1/3 times 1/3 is 1/9. And 1/3 times 2 is 2/3. 2 times 1/3 is 2/3 again. And then we just combined like terms after that distributive process. -4 times -4 is -8. And when you add fractions, you don't add the denominators, just add the numerators when you have a common denominator, which we do have a common denominator of 3. So 2 plus 2 is equal to 4. Then you saw me multiply both sides of the equation by 9. Well, 9 is the lowest common multiple between 9 and 3. Those fractions, right, if you don't want to work with them, get rid of them. And if I multiply by 9, then the division of 9 will cancel away completely here, and 9 divided by 3 is 3, and then 3 times 4 is equal to 12, and again, we then need to combine all of our like terms, and we get 10x squared minus 60x plus 90 is equal to 0. All of these terms end in a 0, so all of those terms are divisible by 10. We divide both sides of the equation, or every term of our equation, by 10. We get x squared minus 6x plus 9 is equal to 0. And because our leading coefficient is 1, then when factoring a quadratic whose leading coefficient is equal to 1, then you're simply looking for factors of the constant that either add, if it's plus, or minus, if this is a negative sign. Factors of 9 that either add or subtract, in this case, add to 6. And you only have two pairs of factors for 9, 1 and 9, and 3 and 3. And -3 and -3 add up to be -6. Why are they both negative? Because they need to add up to a negative number, and when you multiply two numbers which have the same sign, you get a positive answer. If these two factors multiply together to give you an answer of 0, then one of those factors, they're both the same in this case though, one of those factors needs to be equal to 0, so I'm taking that factor, setting it equal to 0, solving for x, getting 3. And again, you're finding a point of intersection, so you're going to have to take that x value of 3 and plug it into one of your original equations and find the other coordinate of your point. So y comes out to be 2, and again, our point of tangency, just like before, is equal to 3, 2. So I gave you two ways to work out the same problem and did a little bit of algebra review, working with you or setting up with you the original example. I hope you enjoyed it. I'm Mr. Tarrou. Bam! Go do your homework. Oh, if you need a review of factoring, I'll put a link to those lessons here as well. No.